So we're still talking about polynomials and complex roots today. Like I mentioned, the book does a lot of overlap, so we're going to go over a few things you've seen before in the context of complex roots. And since we've gone over them before, I'm going to try and do it a little bit more rapidly than I normally would, but if you have questions, slow me down, because it doesn't matter if you didn't get it the first time, you want to get it the second time. So, first technique we've talked about, which is factoring by grouping. We're only showing the basic version of this, but you could have a problem where you have, a sixth degree, and you would group either three groups of two or two groups of three, and it might help. Again, this is a shot in the dark kind of method. If the polynomial succumbs to it, great. If not, you can't be surprised. So the idea of grouping is you have some higher degree polynomial, higher than second degree. I guess it would have to be even. I think it would have to be even. No, it can't be even number of terms. So I guess that means it has an odd degree. I don't really know if that's true. I really like the proof of that. I'm not quite there right now today. So anyway, you look at this and you say, well, if I group these together, make two groups out of this, and then I try and factor as best I can. So x squared, x minus 3, plus x minus 3. I might discover a common factor. In this case, I do. I discover x minus 3 is a common factor. So, using the distribution law, I can take that out. Pause for a second and just stare at that, if you would. So this is different. This is different from a grouping problem that we might have looked at earlier in the book. And there's one crucial difference. One of the factors, well, to begin with, it's second degree, but worse yet, it's irreducible. Yes?
Can you explain where the 1 came from in the x squared plus 1?
Sure. I'm going to try to do it visually, okay? Right, I can always multiply something by 1. Common factor, right? So I always have 1 in there. Does that help? It would have been nicer if this was the. Would have been more obvious if this was the problem, right? I take out a 2 and then see the 2, right? That would be be x squared plus 2. But it's not, so. Okay. So as I said, this has an irreducible, I guess I want to write that word down, irreducible factor. The irreducible factors we're going to see are all going to be second degree. And by irreducible, I mean you can't factor it in reals. Anything in the form x squared plus something has to be irreducible. But now we're dealing with complex roots, so we have more flexibility. In complex roots, this is not irreducible. It's in the form a squared plus b squared, which we can factor as a plus bi times a minus bi. I don't know if I've done this, so I'll try and convince you. We'll just FOIL this. His firsts are a squared. The outer is minus a bi. The inner is a bi. And then we have minus b squared I squared. So these two terms drop out because they're the opposite. I squared, well, I squared is minus 1. So minus 1, you just get a squared plus b squared. So I can factor this as x plus I times x minus I. And that tells me that my roots, are going to be 3, negative I, and 9. Okay, so that's grouping, but finding you have one or maybe more irreducible factors, and still being able to factor it. Any questions about that? Okay. All right. We're going to take another technique we were looking at, I think, Wednesday. It was Monday. And again, apply it now using, with complex roots as an option. We're going to factor using a rational root theorem. Certainly worth a few examples if you're not comfortable with this yet. So the example here is we want to factor p of x equals x cubed minus 2x plus 4. Factor it or find the roots, either way. So this doesn't fit any pattern we know, but we can look at the a, the coefficient of the leading term, and the constant term. And using the rational root theorem, we know that any rational root will be a factor of 4 on the top and 1 on the bottom. So what can that be? That can be plus or minus 1, plus or minus 2 over 1, or plus or minus 4 over 1. So we have 6 possible roots we can check. right, let's go for easy. 1 minus 2 plus 4. That didn't work. Minus 1 cubed minus 1 plus 2 plus 6. That didn't work. So the ones are out. We try positive 2. Since I think that's going to work, I'll even write it up here. So that's 8 minus 4 plus 4. Oh, that didn't work. Looked like it might. But then I can try minus 2. Okay, so this is minus 8 plus 4 plus 4. Aha! 0. So we know at least that minus 2 is going to be a root. Minus 2 is going to be a root. What's the factor? X plus 2, right? We know this will equal x plus 2 times some polynomial. All right, we have 2 strategies for finding out what that polynomial qx is. One of which I said is not necessary. What are those 2 strategies? Do you know what those strategies are? No. You'll need to find out. Connie, do you know? Me? No. Can you hear me?
Yeah.
Oh. Do you know what those 2 strategies are?
No.
No. Okay. Uh-oh, because this is important.
Synthetic division?
Thank you, Henrietta. That's one. Somebody know the other?
Long division?
Thank you, actually. Yeah.
Synthetic division. And long.
Okay, I can do it either way. I need somebody to tell me. Henry, which would you like to see?
Just do synthetic.
Synthetic, okay. So x cubed is 1, the coefficient is 1. X squared has coefficient 0. X has coefficient 2 and 4. I never know where to draw the line here.
Where does 0 oh, because there's no x squared coefficient.
Yes. You have to, if you don't remember that, you will get the wrong answer for sure. Okay, I mean, you know, there's an x squared here. It's just has a coefficient 0, you know. Okay, so what was our root? Was minus 2. All right. Bring one down, multiply, add, multiply, add, multiply. Okay, and make sure you get 0, because if you don't get 0, either the root's wrong or your synthetic division is wrong. And this tells me that this q of x is going to be x squared minus 2x plus 2. Right. You know, of course, when you're doing this yourself, you don't have to fill up 2 or 3 blackboards with it, but all right, enough said about that. Okay, so we've got p of x is now x plus 2 times x squared minus 2x plus 2. Well, I can see one of my roots, but I'm not quite done. And I look at that and I think, I can try boiling it, right? You try kind of going like this. there's a minus there, so these have to be minus and minus, but no. Minus 3x, that didn't work.
Is that where the x plus 2 came from? Where did the x plus 2 come from? Oh.
Popped out of synthetic division. Just for the sake of argument, let's go backwards and do some long multiplication here. So x plus 2. Let's make sure this actually is what we want it to be. So 4 minus 4x, 2x squared, 2x minus 2x squared, x cubed. So x cubed, this is 0, minus 2x plus 4. Is that what I started with? Yeah. Okay, so the synthetic division worked. So I really have no alternative but to fall back on the quadratic formula at this point. Apply it to this quadratic. So, of course, my A is 1, my B is minus 2, and my C is 2. So minus 2 minus minus 2 minus B is 2 plus or minus the square root of B squared, 4 minus 4AB minus 8 all over 2A. 2 plus or minus the square root of minus 4. 2. 2 plus or minus 2 square root of minus 1 over 2. Or 1 plus or minus square root of negative 1. Which is, of course, 1 plus or minus 5. So we have complex roots here. Okay, so I still want to factor this. It's p of x, x plus 2 times x minus each of these roots. X minus 1 plus I, and x minus, yeah, right. Confusing myself, in x minus 1 minus I. Which we could distribute here, x minus 1 minus I times x minus 1 plus I, same thing. Okay, so now, even though it doesn't have 3 real roots, it has 3 roots, I can still factor it. All right, that's using the rational root theorem. All right. Good on this? See, now we almost know everything there is, not everything, but everything we need to know about polynomials, how to factor them, how to find their roots, when possible. There are still a few nits that we want to take in. I think we've mentioned this before. Let's say my polynomial just happened to be this. Okay, if I multiply this out, clearly it's going to be a 5th degree polynomial, having x to the 5th. So I want to see 5 roots, right? But it's already factored. It's x minus 1 times x minus 1 times x minus 1 times x minus 1 times x minus 1. So it seems to only have the root 1. Well, that's true. The complete factorization theorem says it has to have 5, but in order for that to be true, we have to count multiplicity of roots, or multiplicity of zeros. I guess I should write that down. Multiplicity of zeros. Which is to say, yes, 1 is the only distinct root, but it occurs 5 times. So we might want to say, you know, the root is 1, but, you know, in parentheses 5 times. So that's something to be aware of, you know, when looking to factor and looking for roots. The same root could appear multiple times. All right, let's look at an example of that before we go on. Okay, 3x to the 5th plus 24x cubed plus 48x. We're also going to get a review on another technique we talked about, I don't know, a week or 2 ago. But, all right, let's start off with what can we factor out of these? Anybody? 3x? Okay, so I have x to the 4th plus 8x squared plus 16. Okay. That kind of looks familiar. It looks like a perfect square of some sort, but I've got x to the 4th and x squared here. This seems to be another one of those disguised quadratics. You can just do it directly, or we can temporarily, we could substitute. We could say y equals x squared. So then this would become y squared plus 8y plus 16. So we factor that. It's y plus 4 squared. And then we can just substitute back in. Or you can just look at it, stare at it, and go, aha. You have the skills to realize that that's what it's going to be. Okay. Back here again with one of these irreducibles. What would I do with an irreducible like that? Jockey, do you know how to factor x squared plus 4? You can say no.
Are you talking to me?
Yeah.
Oh.
Yeah. Did I mispronounce your name?
It's JC.
JC.
It's okay though.
My apologies, JC. JC, do you know how to factor x squared plus 4 now? You've only done it once, so maybe it didn't sink in yet.
No, I don't.
Okay. JC, you want to answer, Zoe?
X squared plus 4?
Yeah.
Isn't it x plus 2, x plus 2?
It would be great if it was.
It's not though.
So x squared plus 2x plus 2x plus 4. X is in there. Yes?
Would it be x plus 2, x
How
minus
about
2?
x plus 2? Oh, yeah, okay.
Would it be x plus 2, x minus 2?
Okay, let's try that. X squared plus 2x
You can't do it.
minus 2. Oh, good, we're going to get rid of the 2 x's. Oh, minus 4. Now that's x squared minus 4. Okay. All right.
You can't do it.
erase that? Yeah, well, I should have left that word up.
Irreducible.
This complex root.
Irreducible under the reals.
I'm sorry, Alex.
This is the factor is complex roots.
It's gonna need some complex roots, yeah. I guess it went by too fast the first time. Good, because we're gonna review it. Does anybody want to jump in and guess what the factors of x squared plus 4 are?
2, negative 2.
No, we tried that. That didn't work.
Um,
41.
Okay. You put it up again on the board. I think this time it'll sink in. So x squared, a squared plus b squared. Irreducible in reals, but if I multiply a plus bi times a minus bi, this is an important pattern when we get into complex numbers. So what happens? I get a squared plus abi minus abi. Oh, good. You have a plus and a minus, we get rid of that middle term. Then we get minus b squared I squared. But of course, I squared, the square root of negative 1 squared is minus 1. That changes this minus to a plus, and we get back our a squared plus b squared. You really need to know this. Okay? Yes, Harold?
So would it be x plus 2i and then x minus 2i?
Absolutely. Okay? Glad we're over that hurdle. Everybody's got that now, right? Okay. So, of course, I didn't have x squared plus 4. I had x squared plus 4 squared. So I end up with 3x, x plus 2i, x minus 2i, times x plus 2i, x minus 2i. Or we could just mark b squared. So now what are my roots? Well, somebody who hasn't answered. What's one root? Give me one root. Give me the easy root. What can I plug into p of x to get 0? Yes?
You can plug in 0.
0, definitely. That's a root, right? Because I got an x. What's another root? I don't see, I mean, I could try plugging in 1. That would be 3 times 2i times minus 2i. That would be 4 times 3 would be 12. No, it's not a root. Just looking for something I can plug into x to turn this whole thing to 0. I guess I understand. I'm going to call on you in just a second. I guess I can understand. Now we're dealing with complex numbers, and it's like the whole world has gone crazy. But it's really the same thing.
4i.
4i. Let's try that. 3 times 4i, that's the x. Times 4i plus 2i, that's 6i. Times 4i minus 2i is 2i. So 12, 72, 144i cubed. I cubed. It's negative I, actually. Okay. That was a worthy guess. It just wasn't right. Okay. JC, did you want to?
Is it negative 2i and 2i?
Negative 2i and 2i. Okay, let's try that. Let's try negative 2i. Plug it in here, I can plug it in here. Well, if I plug negative 2i plus 2i, that's 0. No, it's 0, right? Same thing, 2i I can plug in here. Okay. The $100 question. It's not real, it's a nickel question. I've got 3 roots, but this is a 5th degree. Where are the other 2 roots? Yes.
Negative 2i and 2i occur twice.
Yeah, they each have multiplicity 2. So 2 plus 2 plus 1 is 5. So I get my roots, I get all 5. That's what I want. That's what I want out of life. So polynomial with the right number of roots. Okay, we're almost beating this horse to death. Please do not call the SPCA up on me. I'm not really beating a horse. And if it's dead, why would they care anyway, right? All right. Last. I stand up here and embarrass myself all day. You could try it. Wouldn't hurt too much. All right. The almost last thing we want to do is we want to kind of reverse this process. We want to say, well, you know, what if we have a bunch of roots, we'll call them, and we want a polynomial for which these are the roots. Well, that's real easy. Polynomial will just be x minus c1 times x minus c2 all the way up to x minus cn. That way, whenever I plug in one of these c's, one of these factors is 0 and the whole thing is 0. Now I could add a constraint here. I could say not only do I want all these to be that root, but let's say I want p of 10, which is not a root, to be 100. I could do that. I can get away with that. The best way to get away, to show you how to get away with that, is to show an example. So here's my example. I want my roots to be I, negative I, 2, and negative 2. But I also want p of 3 to be 25. Okay. Well, let's start off trying this, right? X minus I times x minus minus I, or x plus I. X minus 2, x minus minus 2. Where's my flexibility going to come from? Well, I could multiply this by some constant, right? These would still be the roots. This would still be the polynomial, right? I don't know what a is yet, but I'll get there. Okay, so let's do some multiplying. X minus I times x plus I. This is kind of the opposite of what we were doing before when everyone was having trouble. Does anybody Anybody know what x minus I times x plus I would be? Someone in the back. Okay,
X squared plus 1.
x squared plus 1, okay. Someone else in the back row who hasn't spoken before. What's x minus 2 times x plus 2?
X squared.
You're not in the back row. Ian, Stephen, Megha, Young, one of you know? What's x minus 2 times x plus 2? A minus b times a plus b.
What's the question? What is this? Are
I
you
just
asking
want you to
what is
multiply
minus
x
2?
minus 2 times x plus 2.
It's x squared
X squared
minus
minus
4.
4.
Yeah, I'll put you not in the back row.
Technically, I am in the back though.
You're in the back. Harold is behind you.
Come on, go ahead.
I'll answer for her.
This is an ordered set. There's the front row, the second row, the third. It's x squared minus 4, okay. We could go the next, let's go the next step. What's x squared plus 1 times x squared minus 4? Well, that I can FOIL, right? Oh no, I can't, I couldn't live with myself if I said that. First it was FOIL again. X to the fourth plus x squared minus 4x squared minus 4. So I have the a times x to the fourth minus 3x squared minus 4. Okay, I'm almost done. That's my polynomial, except I don't know what a is. But I do know that p of 3 is 25. So p of 3 would be a times 3 to the fourth minus 3 times 3 squared minus 4. Okay, 3 to the fourth is 27. No, it's not. What's 3 to the fourth?
27 times
3 times 3 times 3 times 3. What is that? Just yell out that number that you all know. Well, 3 times 3 is 9, right? It's like a 9. 3 times 3, 9. 3 times 3, 9. 9 times 9? 81. Okay. I don't know. It's 81 minus 27 minus 4. Okay. Now, you could do this the hard way. You could subtract 27 from 81, and then you'd have to carry and figure it out. But if you add negative 27 and negative 4, you get negative 31. That makes it a lot easier, doesn't it? It says a times 81 minus 31 is 50a. And we know that's equal to 25. So a is just 25 over 50. So finally, I find my polynomial that I wanted to find was, you can write it however you like, 1/2 x to the fourth minus 3 x squared minus 4. You can distribute this, or you can put it over 2. All right, that's finding a polynomial with specified roots. All right. Put that in there. Okay, there's just one more piece of this puzzle. And those of you who are really interested in math and been paying really close attention might have noticed this already. You know, here I had two i's, but I got rid of them. That was nice. I and negative I have a certain relationship that might not be obvious. They're complex conjugates. We talked about complex conjugates before? I think we have. If I have a plus bi, that's a complex number. Its complex conjugate is a minus bi. This is similar to when we were trying to get rid of radicals in the denominator, right? If I had create a little room here. If I had something like this, what do I want to multiply this by to get that radical out of the denominator?
One minus root x.
1 minus root x. Yeah, but I don't really want to change it. That would change it. So I have to multiply it by 1, right? That's 1, isn't it, usually?
Yeah.
Except when is that not 1? Be on the lookout. When is this not 1? When x equals 1, yeah, because that would be 0 over 0. We're not going to worry about that now. Okay, so on top I get 1 minus the square root of x, and on the bottom I have 1 plus the square root of x times 1 minus the square root of x. But the whole reason I did that is because I know that a plus b times a minus b is a squared minus b squared, and I wanted that x squared, that square root of x squared, to get rid of it. So I just end up with 1 minus the square root of x over 1 minus x. Okay, that's a conjugate, radical conjugate. Now we want to look at a complex conjugate, right? I have some complex number, a plus bi, and a minus bi is its conjugate. And what happens when I multiply them? Well, we've seen this already. A squared plus abi minus abi minus b squared I squared. These two cancel. This I squared becomes negative 1, so this just becomes b squared. We get a squared plus b squared. Well, where does that come up? If I have x minus some complex number, and I multiply it by x plus, x minus is conjugate. Sometimes we write that for the conjugate. I know that when I'm done, whatever is over here, there will be no imaginary component anymore. It will be real. Let's see an example of that. So 5 plus 3i. What is the complex conjugate of 5 plus 3i? 5 minus 3i. Okay. I could do all the work, or I could just use my pattern. Right. I'm going to do all the work. 25 plus 15i minus 15i minus 9i squared. All these cancel. 25 minus 9i squared, the I squared is minus 1, so plus 9, 34. Okay, how is that going to help us? Well, here's the problem. Keep that technique in mind. Here's the problem. I want a polynomial that has roots 1/2 and 3 minus I, and I want it to have real coefficients. In other words, clearly, like one of my roots could be x minus 1/2, or it could be 2x minus 1, because that's easier to deal with. And another one of my roots will be x minus 3 minus I. But I'm going to end up with an imaginary component here, and I want to get rid of that. So how do I do that? How do I get rid of that I? Yes, Harold?
Do you multiply it by 3 plus I?
Did you say divided by 3?
I said multiply it.
Oh, okay. Plus I. Well, let's give that a chance, see what happens. Let me leave this. This is all real, so multiplying it, won't change it. So let's just multiply these two. So how am I going to do that? I guess, let me distribute this over here. So I get 3x minus 9 minus 3i. Plus, and now I, xi minus 3i minus I squared, which is just plus 1. Okay, so let's go 3x plus ix minus 9 plus 3i minus 3i plus 1. Okay, so these cancel, that's nice. Minus 9 plus 1 is minus 8. 3x plus ix minus 8. We almost did it. We still have an I in here. Good try, though. I mean, I think you're on the right track. Anybody besides Alex have an idea here? I'm not trying to embarrass you. Just trying to give some people who are out there, I know they have the answer, and they're afraid it might be wrong. That wasn't so bad, Harold, was it? You almost got it, right?
Yeah.
You're not gonna, have to cry after class. I just want everyone to know that. It's not so bad,
Yeah.
I mean, it was actually a pretty good idea, because these disciplines are on the right track. Carlos?
Was it 3 minus I?
Okay. Let's try that. Okay, so 3x minus 9 minus 3i plus minus ix minus 3i plus I squared, so that's minus 1. We still have this ix thing here. I'm having trouble getting rid of it. I think the reason you're having trouble finding this is because you think the rules are something that they're not. All I said was, I want a polynomial. I want these to be roots. I didn't say I want them to be the only roots. I just said I want them to be roots. So if you can add another root that would help, that might do it. Is there another root I could add to this that would probably help? Maybe that's what I should have asked people to guess. What root should I add that will help the final polynomial to have real coefficients? How about the complex conjugate? Okay. So, all right, let's spoil this. X squared. Outer is minus 3 plus I x. Inner is minus 3 minus I x. And then plus 3 minus I times 3 plus I. Well, that's good, because that's going to be real, right? Right? That's going to be 9 plus 1 or 10. That's real. Minus 3x minus ix minus 3x minus plus ix. Oh, these are going to cancel. I get x squared minus 6x plus 10. Hooray! So there's a moral here, which is if you want a polynomial with real coefficients and you've got a complex root, you need its conjugate as a root also. That's how you get rid of those pesky imaginary coefficients. This problem we're not quite done. We still need to multiply by 2x minus 1 because of this root, but yeah, you could do that. I feel like we've made great breakthroughs today. And I've been wrong before. Okay, any questions about any of this? This is kind of the end of just plain old polynomials. We're not done with functions by any stretch. And functions until the end of the year. There's a homework assignment for Monday. You can take a stab at that. And a couple people wanted to see me today. I'll be in my office from about